Hello, this is Sherif Abdelmohsen. I'm presenting the paper titled Extending the Passive Actuation of Low-Tech Architectural Adaptive Systems by Integrating Hygroscopic and Thermal Properties of Wood on behalf of Ali Ibrahim and myself from the American University in Cairo, and Walid, Omar, and Akram, Zayan from Alexandria University. The problem in this paper is related to the studies that have addressed the programming and prototyping of wood motion response using physical experimentation, testing wood response in real weather conditions, and using numerical simulations to estimate wood motion response. Hygroscopic properties of wood are related to its ability to absorb and hold water, causing swelling and shrinking upon water release. And wood, similar to other materials, undergoes physical transformations that are directly proportional to increased temperature. So this is due to an increase in spacing between wood molecules as they improve the vibration magnitude at rising temperatures. These motions are typically evaluated as a coefficient of linear thermal expansion, which is a function of the relative change of proportion caused by change in temperature. Coefficients of thermal expansion of fully dry wood are strong across all directions, which expand with heat and contract upon cooling. Work on the effect of wood material variance on temperature change was typically performed in very limited quantities, and so this paper extends the passive actuation of adaptive systems in climates where humidity and/or temperature variations are dominant. Typically, if there are significant changes in the temperature of the environment, this results in deformation changes due to an increase in the associated humidity by shrinking and swelling, which exceeds small thermal expansion and contraction values independently. Dimensional changes induced by temperature variations are negligible for the daily use of wood. Although expansion is not normally significant, the influence of temperature on wood strength is essential. High temperatures may result in both temporary and permanent decreases in timber strength. Although local thermal radiation affects the reactive behavior of wood veneer by influencing relative humidity, air convection temperature changes generate more general and stratified alteration. The relative humidity of the atmosphere can be improved without excessive moisture input. For our approach, the effect of temperature on wood veneer typically differs from the effect of humidity. We conducted, therefore, 2 pilot tests to delineate the basic effect of each on wood veneer samples. Typically, the literature shows that temperature can impact materials by increasing their porosity level to gain more moisture. This can be conducted through either increasing ambient air temperature or by applying direct sprayed water with varying water temperature. This figure in the first pilot test shows the bending effect on a wood veneer sample upon applying both hot water spray and tepid water spray. Larger deflection was observed with the hot water sprayed sample. For the next pilot, upon applying and increasing humidity on the sample, the exposed surface acts as an active surface by swelling directly based on the amount of humidity applied. Upon increasing temperature only, the exposed surface shrinks, implying that the porosity level increases while having little moisture. This results in a deformation of the sample and the loose surface, in addition to decreasing the amount of moisture of the exposed surface due to increasing the temperature level. We conducted 3 experiments under specific wood parameter conditions and 3 varying humidity and temperature conditions. We used a sealed chamber for the containment of the wood samples and a vertical clamp fixed on a horizontal plane to avoid friction. A digital camera was used to record the motion of wood using video and time-lapse images. We recorded the average deflection and response speed rate for each experiment. For the first experiment, which used varying humidity and constant temperature, the primary observation here is that based on the principle of equilibrium moisture content, there was a noticeable change in motion of the sample based on its absorbable nature. In the second experiment, where we varied temperature and had humidity as constant, the main observation is that the more the heat gained by the sample, the higher the fiber ability for hydro expansion. Based on the principles of the coefficient of thermal expansion of wood, it was shown that higher levels of temperature are significant parameters. In the third experiment, we varied both humidity and temperature. We observed a higher deflection and response speed under high relative humidity above 80% and upon increase in temperature above 35 degrees Celsius. And this demonstrates the combined effect of humidity and temperature as 2 significant parameters in the shape-shifting process. The more heat gained for the sample, the more the ability of the fiber for hydro expansion, which allows the pores to gain more moisture. Accordingly, when humidity is applied, the sample could absorb more moisture than before raising humidity levels. This becomes one of the distinguishable characteristics of this hybrid sample. In terms of implications on facade morphology and design exploration, it was apparent that computationally the integration of temperature and humidity as two main input parameters introduces variations to the design exploration process of facade morphology, where two output parameters are physically in play: shape-shifting in terms of bending morphology and motion response rate. We introduced a case study of an office building in Kuwait City with facade dimensions of 25 times 12 meters. We used Grasshopper to model and simulate the hygromorphic performance of modular facade skin panels based on weather data using temperature and humidity as two main input parameters. Thermal simulation was conducted in different time intervals, and the resulting deflection morphologies and motion response rates were recorded. In terms of the general discussion, the added value of introducing temperature in this setting involves its role as a key regulator in the degrees of deflection and motion response rates of the wooden samples. This involved three states. In the first state, deflection occurred based on the absorbable capacity of the sample and its direct response to varying levels of humidity. In the second state, the deflection and motion response rate were more controlled and subtle. And in the third one, yet another pattern of deflection was observed where temperature acted as a catalyst and accelerator for deflection and motion response rate. We also observed that temperature was shown to play a role in accelerating, decelerating, or stabilizing deflection of a given sample. And also in terms of shape-shifting response, they could extend to include different climatic zones where variations in humidity and temperature can result in emergent shape-shifting mechanisms. Other parameters such as lamination, layer thickness, and fiber orientation, and ratio and type of wood could be varied also to produce further morphologies. Thank you very much.